Morning, everyone. Welcome back to Trig Proofs. Hooray! Some of my absolute favorite stuff. We ended the last lesson Friday. I know it was a long time ago. We ended the last lesson on Friday with this question, and we were trying to verify this identity using a Pythagorean identity, verify this identity using specifically a Pythagorean identity. And all the Pythagorean identities involve a 1 and some squared trig. We had no squared trig. So what I did was I forced a Pythagorean identity by multiplying by the conjugate of 1 minus sine of x. Because anytime you multiply a plus b and a minus b, you are going to get a squared minus b squared. And in this case, that was 1 minus sine squared x. There was a lot of blank faces when I did this. Because you guys are probably wondering, how did I recognize to do that? How did I know that that's what I should do? Well, the answer is lots of practice and always on the lookout for Pythagorean identities and knowing that a good number of them are the difference of two squares. 1, 2, 3, 4 of them are the difference of two squares. So they're going to jump out at you a lot if you recognize them. So you got to know them. So I know these two by heart. I told you that. And the other ones I don't know by heart, but I see things with ones and squared trig and I think that might be a Pythagorean identity. And I'll rebuild it. And if it is, woohoo, I'll pursue that avenue. And if it's not, I will do something different, So again, how did I know to do that? Well, I know I'm trying to get to secant x, which is 1 over cosine x, right? This fraction already has an over cosine x. So one of the thought processes is, how do I make this be an over cosine x? And again, the way that we relate sine of x and cosine of x with the Pythagorean identity is knowing that sine squared x plus cosine squared x is 1. So this is what you get if you subtract sine squared x from both sides. And also, that'll give me cosine squared x on the bottom, which would cancel that cosine x on the top. This would be what I would consider the elegant way of approaching this question. But that doesn't mean it's the only way. Think about if you had to drive from your house to your friend's house. You know where you're beginning, and you know where you're ending. But more than likely, there's more than one way to get there. Trig proofs are the same thing. You could see where you're beginning, and you could see where you're ending, and you're allowed to think about what would be the best way to get you from here to here, or maybe you're just going to hope, and you're just going to start driving. Sometimes that happens. Let's approach this question in a different way. Let's say you are not very good at seeing, ooh, if I multiply by 1 plus sine x, I'm going to get cosine squared, and that's going to be, maybe you don't see it that way. What else could you have done? Well, think about it in terms of basic mathematics. Don't think trig. Basic mathematics. I see two fractions with a minus sign in between them. What is something else I could have done? Two fractions, minus sign between them. Don't think trig. You mean find a common denominator? Yes. So we could have found a common denominator and approached it that way. So in order to pull that off, you have to remember that in order to find common denominators, it's always done through multiplication. This doesn't factor. This doesn't factor. These two denominators have absolutely nothing in common. So when two denominators have nothing in common, like an over 3 and an over 5, how do we find the least common denominator? Yeah, you just multiply the two denominators to each other. And that's how I did this question with second period today. Boop. This way, I could show both classes both ways. I showed them what I did with you on Friday. This is what I did with them today. I multiplied the top and bottom of this by cosine x. I multiplied the top and bottom of this by 1 minus sine x. I distributed the negative sine x, and it was negative because I changed it to a plus negative sine x over cosine x. So I distributed the negative sine x, and it gets me here. When you combine these fractions that have a common denominator, on the top, hopefully it jumps out at you, there would have been a cosine squared x plus sine squared x. This is the Pythagorean identity. Cosine squared x plus sine squared x is 1. There's the minus sine x. The 1 minus sine x cancels off the top and bottom, leaving you 1 over cosine x, which is secant x. So a completely different way of doing this trig proof. Okay? Basically, at this point, you have learned 2 tools for trig proofs. One of them is be on the lookout for conjugate multipliers. They're going to give you Pythagorean identities. Where is it? Right there. Be on the lookout for conjugates that when multiplied give you a Pythagorean identity. Another thing to try, when you see fractions with addition or subtraction between them, look for common denominators. Okay? So those are two really powerful, commonly used tools in trig proofs. Now this one. It doesn't matter which side we work. We can either go from left to right or we can go from right to left. It doesn't matter which one, and it's the same amount of work either way. So I'm going to go from left to right. This is a single fraction. So it's not like I can try to find a common denominator. This is a single fraction. And the only thing that you're allowed to do to a fraction is multiply on the top and bottom by the same number, right? So we know that we're starting with this. We know basic mathematics tells me the only thing I could do to a fraction is multiply to the top and bottom, the same number. And we know we're trying to get to here. Clearly, there must be a way to relate cosine of x with sine of x. And the only way that I know of that can relate cosine of x with sine of x through multiplication, because remember, you're going to have to multiply to the top and bottom, is by using the idea that cosine squared x, or theta, is 1 minus sine squared theta. So again, this and this are darn near this Pythagorean identity. So it doesn't matter which side we work, the left side or the right side. Our goal is to get to this statement so we can cancel a cosine somewhere. I'll work on the left side. What you're supposed to see, hopefully, is that if you multiply this by its conjugate, what you're going to get is a squared minus b squared, or 1 minus sine squared theta. I'm going to leave the numerator factored. And hopefully you've started to commit some of these Pythagorean identities to memory. 1 minus sine squared theta is cosine squared theta. Well, you have to memorize some of them. I have the ones for sine and cosine squared memorized. And it's by accident. They're so insanely common that you will accidentally memorize them. Yes, sir? Oh, crud. Hate when that happens. And this cosine cancels one of those two cosines, and you're left with the right side. Yay! 1 minus sine theta over cosine theta. Ta-duh. So again, I have, where are they? These two memorized. And obviously that one, because these are simply subtraction. The other 4, well, no, I don't have them memorized. I know they exist, and I know how to get them. That's enough for me. These are the most common ones. So you will accidentally get them memorized. Trust me on that. That doesn't mean you shouldn't try to memorize them. You should. Maybe put them on some flashcards or something. Do what you got to do to memorize it. Pretend it's that new TikTok dance that you like so much. If you have the ability to memorize that, Or that new Taylor Swift song and you want to memorize the words. You love Taylor Swift. Noah Duncan loves Taylor Swift. He is definitely a Swiftie. He's got Taylor Swift on the front of his binder. You should see it. Anyway, try to memorize them. Because bad news, folks. There is no way around it. You have to memorize all 8 of these.
Really?
Yes.
You have them memorized?
Nope. Well, I could tell you how I rebuild them when I need them. It's going to sound a little ridiculous, but I leave myself some breadcrumbs that helps me rebuild these identities when I need them. I have memorized some of them. I have this one and this one memorized. So yeah, I've had to memorize some of it. I have these 2 memorized, and from those 2 identities, I can build everything else with some strange tricks that I've taught myself. Let's go for the easy ones first. Not even trickery. These 2 come directly from using a Pythagorean identity substitution. Replace this with 1 minus cosine squared u, and combine your like terms, you'll get that. Replace this with 1 minus sine squared u, and combine your like terms, and you'll get that. So those are really easy. So what did I put a star next to? These are your double angle identities. They are how you would evaluate sine or cosine if you just decided to double the argument. For example, let's say you had sine of 30 and you wanted to double it to sine of 60. You could draw a triangle for 60 degrees, right? Or you could use sine of 30 times cosine of 30 degrees, obviously, and then double that, and you would get sine of 60 degrees. This identity says sine of 2u or 2 theta or 2x or whatever is, I like that idea. Sine of 2 theta is 2 sine theta cosine theta. It's an easy one to memorize. 2 sine theta cosine theta. I could show you where it comes from, but it requires geometry, and I'd have to break out a compass and a straight edge and distance formulas, and it's just not pretty. I'm not doing that. You are welcome to watch a YouTube video like I had to do to see where it comes from. Anyway, sine of 2 theta is 2 sine theta cosine theta. Cosine of 2 theta is cosine squared theta minus sine squared theta. Again, if you would like to know where it comes from, there are YouTube videos on how to derive them, but it requires a compass and the distance formula and all kinds of geometry. Let's see who's at the door. I use this identity to rebuild this identity right here. And here's how. I pretend that this says, and this is just my trail of breadcrumbs, sine of u plus u. The only way that you were going to get a 2 here was if the 2 things that you added were exactly the same, right? See the similarity? Now the order of this multiplication is backwards, but that doesn't matter because the order of multiplication doesn't matter. Yes?
But on the top, A and B are different.
I'm aware. That's why I said that this is the trail of breadcrumbs that I leave myself. But if they weren't different, say they both said u, this would say sine u, cosine u, plus cosine u, sine u. Okay? So it's how I know this formula it comes from here. And here's what this tells me. The sine sum identity, because this is the sum of two different angles. This could be like sine of 20 degrees plus 30 degrees. Requires me to put sine and cosine together, use the same symbol that I had here, and then put sine and cosine again together, but in the opposite order. I tell myself, sine, same. This identity shows me that it puts sine and cosine together. Sine, same is what I tell myself for the symbol. So if I see a minus sign between them, I know I need a minus sign here. Sine, same. I'm just telling you my tricks that I've taught myself. This identity shows you that cosine puts cosine with cosine and sine with sine. So if you imagine this says cosine of u plus cosine of u, cosine of u plus u, what you can see is that it multiplied a pair of cosine u's and a pair of sine u's, and it uses the opposite symbol. So sine same, which tells me cosine is not same. I know all this sounds ridiculous. This is just the ways that I've taught myself to memorize these things. Cos, cos, sine, sine, opposite symbol. Cos, cos, sine, sine, opposite symbol. There's no way around it. Figure out a way to commit them to memory. I use these two to tell me how to build these by memorizing some basic structures. This shows me that sine, sum or difference, puts sine and cosine next to each other. This shows me that cosine, sum or difference, puts cosine together and then sine together. This shows me sine uses same symbol. This shows me cosine uses opposite symbol. That's the best I could do for you. Make some flashcards maybe. All right? Unfortunately, no, because sine is odd. So putting the minus sign in between for sine puts a minus on the outside, but that doesn't even make any sense here because we're talking about making the entire angle negative when you say odd. So no. Nope. Flashcards. Yep. So what can we do with it? We can evaluate pi over 12s now. That's what we can do with it. Yay, pi over 12s. So let's do it like this. I'm not going to do this because how many of you instantly knew this was true? Nobody. Exactly. Neither did I. Okay. So how would I have done this? I would have figured out what this is in degrees, which I know I've been telling you this whole time don't work in degrees, but your life will be easier if you do these kinds of things in degrees. Here's why. What is pi over 6 in degrees? 30 degrees. So then what is pi over 12? 15 degrees. This is 5 times 15 degrees, which is 75 degrees. And I quickly can see two special angles, that add up to 75. 30 and 45. One of the ways that you're going to help yourself memorize your identities is if you write the identity every time you go to use it. Sine, cos, cosine, same symbol. Again, I know that sine of 2 theta is 2 sine theta cosine theta. That tells me the sine sum or difference identity puts sine and cosine next to each other and same symbol. Then you just have to remember to swap. Breadcrumbs. oh, I'm going to be evaluating sine and cosine at these two angles. And since I don't have my unit circle memorized, I'm going to have to draw those two special right triangles. One at 30, one at 45. Across from 30 is a 1. There we are. All right. So I'm going to write out my identity with my 30 degrees and my 45 degrees in it. Sine 30 degrees, cosine 45 degrees, same symbol, swap your trigs. Cosine 30 degrees times the sine of 45 degrees, and evaluate. Y over r at 30 degrees gives me 1/2. Cosine at 45 degrees is the same as sine at 45 degrees. It's going to be 1 over root 2. Cosine 30 degrees is x over r, root 3 over 2. And sine 45 degrees, 1 over root 2. These will have a common denominator, which is nice. But it gets me 1 over 2 root 2 plus root 3 over 2 root 2. You need to rationalize your denominators. So you're going to have to multiply the top and bottom by root 2. On the top, you're going to get root 2 plus root 6. Order of addition doesn't matter. On the bottom, root 2 times root 2 is 2. So this says 2 times 2 over 4. There you go. So that is sine of 75 degrees. Yes, sir?
Why didn't you just multiply the two sides for each other?
Why didn't I just multiply the two sides first?
It's 1 over 2 times 1 over root 2.
I did.
Wouldn't I just be 1 over 2 root 2?
It is.
Yeah.
Yeah.
Other side is going to be root 3 over 2 of root 2.
Which is right here.
Why'd you multiply everything?
I was just rationalizing the denominator.
Oh.
So instead of saying 1 plus root 3 over 2 root 2, because that sounds and looks horrible, you just rationalize your denominators, and what you get is root 2 plus root 6 over 4. Neat. So now you have the ability to evaluate any trig at a pi over 12. Any of the pi over 12s. There are 24 of them. Yep. And now you have the ability to evaluate sine, cosine, and you know what's interesting? You know what we didn't have in the identities? The tangent double angle identities. Or the tangent sum or difference identity. Whatever shall you do if you run across a tangent double angle? What's that? Sine over cosine. Use the division. So if you need to do tangent of 2 theta, just do sine 2 theta over cosine 2 theta. Yep. Same thing for tangent of alpha plus beta. Sine of alpha plus beta over cosine of alpha plus beta. Yep. Hey, look, another pi over 12. The 7th one. All right, so hopefully you realize real fast that all pi over 12s are multiples of 15. So what is 7 times 15? It's 105 degrees. Two numbers that add up to 105 that happen to be special. 45 and 60. That'll do it. 45 degrees and 60 degrees. Again, if you write the identity every time you go to use it, you will eventually accidentally memorize them. Cosine goes cos, cos, sine, sine, opposite symbol. That means I'm going to need the right triangle for 45 and the right triangle for 60. If this is 60, across from it's the root 3. There we go. Cosine of 45 degrees, same as sine of 45 degrees, 1 over root 2. Cosine of 60 degrees, 1/2. Sine of 45, we've already said, 1 over root 2. Sine of 60 degrees is root 3 over 2. Remarkably similar to the last question. Difference is now there's a minus sign in between them. So when you rationalize your denominators, multiply the top and bottom by root 2. This time you are going to get root 2 minus root 6. Over 4. And root 2 is clearly smaller than root 6. This answer is negative, which makes perfect sense because 105 degrees is in quadrant 2, where cosine is negative. I'm sorry? Why did we do differences? I didn't. I used the cosine sum identity. But the sum identity has a minus sign in it because cosine uses the opposite symbol. Now, I could have done differences if I really wanted to. I could have done, trying to see it, what are some numbers that, let's see. I could have done 135 minus 30. That'll give me 105 also. Because 135 is 3 45s. So is that 3 pi over 4? Yep. Yeah, I could have done 135 minus 30. Would give me the exact same answer. Just would have been a couple different triangles. So clearly, this root 2, root 6, and 4 are inherently part of the triangle that has 15 degrees inside it. Yes, Adi. Shh. If you ever had more than 2 that add together, which you could just say that you could combine 2 of them and just say it's still just 2. So like if you said like 30 plus 30 plus 45, we go, well, that's 60 plus 45. Okay. And if you feel like that's a lot of identities, just be happy you didn't also have to know the half-angled identities. You don't have to know the power reduction identities, because there's a lot more identities than what you've been shown. A lot more. I'm sorry? I believe these are the only ones. I believe. I don't know. No, there's lots. We haven't even touched polar. Yeah, we haven't even touched polar. Yeah, there's more than 313. Nope. I wish. Okay, here's one that we know to be true. It's just showing you that sine and cosine are complementary to one another. Remember, this is 90 degrees. Let's just say x is 40 degrees. This says sine of 50 degrees equals cosine of 40 degrees, which makes perfect sense because 40 and 50 make 90. Now we're going to use our sine difference identity to confirm that it works. I mean, you could just graph it and use transformations, but we're going to confirm using the difference identity. So again, write them every time you're going to use them. Sine cos, cosine, same symbol. That means this thing on the left, I'm going to do this in blue, can be written as sine of pi over 2 cosine x minus cosine pi over 2 sine of x. It's not a special right triangle, it's a quadrantal angle, but boop, it be right here at pi over 2. The coordinate on the unit circle will be 0, 1 with the radius of 1. Sine is y over r, 1 over 1. Cosine is x over r, 0 over 1. But 0 times sine of x is 0. And 1 times cosine x is cosine x. So we could demonstrate this graphically, or we could use the sine difference identity. Any questions so far today? No? Okay. Yeah, you're going to want to make flashcards. Still see a few pencils scribbling. Yes, ma'am.
So, okay. So the first one on like that second portion from sine is
This?
yeah, that one. So that's just because it's on the quadrantal.
Well, this is part of the identity. I was just filling out the identity. So this is the identity. You have to know it. That's alpha, that's beta. Okay. Alpha and beta are always positive numbers. We have different formulas for plus and minus. Alpha and beta are always positive numbers. Cool? So what can we do with it? Well, maybe we can play some games. Like this. Little trig games. Sine of alpha is 4 over 5, but it's in quadrant 2. Then what's the missing side length? Or better yet, how would we find it? Pythagorean theorem. You would do the Pythagorean theorem, and you would get 3. But I'm in quadrant 2, so negative 3. This is the 3, 4, 5 right triangle. Very common on the SAT. We also know that sine of beta is 1/2 in quadrant 1. Again, if you do the Pythagorean theorem, what you're going to find out is that this missing side length is root 3. Now, let's figure out what cosine of alpha is. Cosine's x over r. Looks to me like it's negative 3/5. Cosine of beta. Bless you. Beta is, cosine is x over r, but I'm at beta now, so root 3 over 2. We now know sine and cosine of alpha. We also know sine and cosine of beta, which allows us to instantly fill out these things. I am going to write the identity because, again, the more you write it, the more likely you are to memorize it. Cosine is cos, cos, sine, sine, opposite symbol. Cosine of alpha is right there. Cosine of beta is right there. Sine of alpha was given to us in the words. It's 4 over 5. Sine of alpha beta was given to us in the words. It's 1/2. The denominators will already be rationalized. So we just combine our fractions. Negative 3 root 3 minus 4 all over 10. Isn't that fun? Yes?
You also know that angle beta is 30.
Yes, we do know that angle beta is 30 degrees, pi over 6. But it doesn't really help us much because the 3, 4, 5 is not a nice angle. It's pretty ugly. Sine of alpha plus beta. Sine cos, cosine, same symbol. But then we can just fill it out because we know everything. We know all of its stuff. Sine of alpha was given to us. We found cosine of beta, literally directly above, root 3 over 2. Cosine of alpha we found, negative 3/5. And sine of beta was given to us in the words, 1/2. So once again, denominators are already rationalized for us. Gives me 4 root 3 over 10 minus 3 over 10. So 4 root 3 minus 3 over 10. I know it's a lot to memorize, but how do you feel about at least the mechanics of it? The mechanics may be a little tedious, but not difficult, right? I mean, we're just evaluating trigonometry the way we've always done. So we have to memorize, yes. There's no way around it. Or memorize a couple pieces like I did and leave yourself clues as to how to rebuild the rest. I'm going to turn the page just because I'm curious. I don't even know what's on the next side. Nope, I did not. Woo! Yeah, I can't do that in less than 3 minutes. So, we'll save it till tomorrow, nerds. Thank you.